For decades, robots were powerful but trapped in rigid routines, unable to deviate from their programmed paths. Think of the classic factory robot: huge arms, perfect precision, repeating the same task thousands of times without fail. This revolutionized manufacturing, making it faster, cheaper, and significantly safer for human workers. But these robots only excelled in tightly controlled environments, where every variable was known and managed. Everything had to be exactly the same, every single time, without any deviation. If anything changed, a part out of place, a person nearby, the robot would either stop or malfunction, unable to adapt. They couldn't adapt or improvise, making them inflexible. Their intelligence was just a strict script move here: grab this, turn, release, and repeat. That's why you never saw them outside the factory, confined to their predictable environments. The unpredictable real world was simply too much for them to handle. They were like musicians who could play one song perfectly, but nothing else, unable to improvise or adapt. To break out of that box, robots needed to do more than follow instructions. They needed to learn and adapt to new situations. That's where the next chapter of robotics begins, with machines that can think and learn. Enter physical AI. The idea of giving robots the ability to see, think, and act in the real world. It's about bridging the gap between digital intelligence and physical action, so machines can truly interact with their surroundings, not just follow preset instructions. Imagine making a sandwich, spotting the bread, grabbing the knife, and adapting if something's off, like if the bread is missing, or the knife is in a different spot. You adjust without thinking, using your senses and experience to solve problems on the fly. Physical AI aims to give robots this same flexibility and adaptability, so they can handle unexpected changes and new situations just like humans do. It combines a physical body, motors, arms, sensors, with an AI brain that processes information about the world, making sense of what's happening around it. First, perception. Robots use cameras and sensors to build a 3D map, recognize objects, and understand their environment, much like our own eyes and brain work together. Second, decision. The AI brain chooses what to do next, planning actions based on the situation, weighing options, and predicting outcomes before making a move. Third, action. The robot moves, grips, and manipulates objects, carrying out its plan with precise movements and adjusting as needed. Crucially, this is a loop, constantly seeing, thinking, and adjusting. The robot never stops learning from its environment and its own actions. If it starts to drop a cup, it can catch itself and correct, reacting in real time to prevent mistakes or accidents. No more rigid scripts, just continuous adaptation. Robots can now respond to unpredictable scenarios, working safely and efficiently alongside humans. That's physical AI. See, think, do, repeat. It's a cycle that brings machines closer to true autonomy. It's the foundation for robots that can handle the real world, and it's changing everything, opening up new possibilities for how we live and work alongside intelligent machines. The real breakthrough in robotics is flexibility. Robots that can handle variety, not just endless repetition. This is what sets the new generation of robots apart from their predecessors. Old robots were rigid and failed if anything was different from their programming. If the object changed shape, color, or position, the robot simply couldn't cope. Physical AI robots, on the other hand, learn general concepts, like pick up an object, not just pick up this blue box. They're designed to adapt and respond to new challenges. It's like teaching a child what a dog is, not just showing them one poodle. Once they understand the idea, they can recognize all sorts of dogs, even ones they've never seen before. These robots are trained on massive amounts of data, learning to recognize and grasp all kinds of objects, big, small, soft, or hard. They develop a kind of intuition. Round things roll, heavy things need a firm grip, and delicate things require a gentle touch. This intuition is built from experience, just like humans learn from trial and error. This lets them generalize to new situations, so they're not stumped by something unfamiliar. When faced with a new item, they analyze its shape, size, and even texture, then figure out the best way to pick it up. They can adjust their grip and approach on the fly. They improvise, applying general knowledge to specific problems, making them far more adaptable than ever before. That's the secret sauce. Robots that can work in our messy, unpredictable world, where nothing is ever exactly the same twice. It's a huge leap from the rigid, single-purpose machines of the past, opening up new possibilities for automation. Flexibility is what makes modern robots truly useful, allowing them to assist humans in real-world tasks and environments. And it's only possible with physical AI, which is transforming what robots can do and how they fit into our lives. Why is robot progress suddenly exploding? It's a perfect storm: better hardware, smarter AI, and connected learning. Powerful chips, GPUs, let robots process huge amounts of data in real time. What once needed a room full of computers now fits on a chip inside the robot. Shared learning means robots can upload new skills to the cloud, instantly teaching the whole fleet. Instead of one robot learning alone, hundreds learn together. Large AI models trained on vast data give robots a baseline understanding of language and the world. Now you can say, "Pick up the red apple," and the robot gets it. These advances are converging, fueling the leap in robot intelligence. That's why robots are suddenly everywhere. The pace is only accelerating. Teaching robots in the real world is slow and expensive. Enter simulation, a digital playground where robots can practice millions of times, fast and risk-free. Engineers create virtual twins of robots and environments, complete with realistic physics. The robot's AI sees and acts in this world, learning from endless trial and error. A day's practice in minutes, no broken vases or wasted time. Simulations allow for endless variety, different lighting, objects, and scenarios. Robots learn general principles, not just memorized routines. Once the AI masters a task in simulation, its brain is transferred to a real robot. The skills translate surprisingly well. Simulation is a game changer for rapid robot learning. It's how robots are getting smarter, faster than ever. A robot needs more than strength. It needs to see and understand. Old robot vision was basic, simple shapes, easily confused. Now deep learning and advanced sensors give robots 3D vision. They see not just flat images, but volumes, distances, and relationships. AI models trained on billions of images let robots instantly recognize objects: a mug, a keyboard, a banana. They understand context. The banana is on the table next to the keyboard. This comprehension lets robots follow natural language commands. Hand me the water bottle on the counter. The robot finds the counter, spots the bottle, and plans a grasp. Seeing, understanding, and acting are now seamlessly linked. This is the cornerstone of modern physical AI. It's why robots are finally useful partners in human spaces. Physical AI is already transforming industries. Warehouses are the prime example. Robots sort, pick, and pack millions of items, working alongside people. Mobile robots bring shelves to workers. Robotic arms pick products from bins. They run 24/7, boosting speed and efficiency. Hospitals use robots to transport supplies and handle lab work, freeing up staff for patient care. In labs, robots perform repetitive tasks with precision, reducing errors. Agriculture uses robots to pick fruit and target weeds. Construction sites deploy robotic dogs to monitor progress and safety. Robots aren't replacing humans. They're taking on dull, dirty, and dangerous jobs. Humans focus on complex problems, while robots handle the rest. It's a powerful partnership, already reshaping work. Despite progress, the real world is still a huge challenge for robots. Warehouses and labs are semi-structured, orderly, but not chaotic like a city street. The toughest problems are rare, unexpected events, a crushed box, a leaking bottle. Humans adapt instantly. Robots can get stuck or confused. Manipulating soft, flexible objects like folding laundry is still extremely hard for robots. Our world is full of unpredictable, deformable things. Safe, seamless interaction with humans in crowded spaces is another frontier. Robots must learn social cues, waiting in line, yielding at doorways, recognizing when someone needs help. These skills take humans years to master. Until robots get better at this, they'll stay in controlled settings. The journey to true adaptability is ongoing. What does this mean for us? Work is changing. Robots will keep taking on repetitive, dangerous, or physically demanding tasks. Humans shift from manual labor to supervising, maintaining, and improving robot fleets. New skills are needed: installing, programming, and collaborating with intelligent machines. In medicine, construction, and beyond, robots amplify human abilities. The future is humans and machines working together, not against each other. As robots get cheaper and smarter, they'll help at home, in restaurants, and in public spaces. This won't happen overnight. It's a gradual, practical revolution. It's not science fiction, but real progress solving real problems. We're at the dawn of the age of physical AI. The future is being built, one task at a time.